right, we can start. Hello everyone. Today we have Dr. Nasser and his PhD student Al Bashidi, and from Clemson University with us. They will talk about the machine learning, and not only what machine learning is. They will show us how it can change the way we work in building and construction fields through like a real life example. They will show how machine learning can help us to understand things better and discover new way to doing things. And let's dive in and see how the machine learning can make a big difference in our field. So the stage is yours.
Perfect. Thank you very much. Hello, everybody. I'm Zain Nasser from Clemson. I'm joined with my PhD student, Mo Bashiti, and both of us will be talking a little bit about machine learning and how we can use it in fire engineering problems. This presentation, we will mainly talk about big ideas, general ideas, and then towards the end, we'll focus on a case study specific to fire engineering. We both come from Clemson, and this is our campus. As you can see, it's a beautiful campus. If you happen to have a chance to come to the US or South Carolina, please pass by. I promise you it will be brilliant. So the big idea for this presentation comes really from the following. If you have in our construction field, every construction firm, every year, this is how much data they generate. So they generate 125,899,906,842,624 bytes. This is one firm every year. This is a massive amount of data. If you take this data and you try to visualize it, this is how much this data would look like. That's about 500 billion pages of text. Or if you have floppy disk or CD-ROMs, it's about 1.5 million disks. So as you can see, there is a lot of data, and this data we collected, and surprisingly, we only use 5%. So from each firm, from all the data we collect, we only use 5%, we throw 95%, and with this 5%, we can do the amazing things that you can see. So the question becomes, well, what if we use 7% or 10% or 20%? What else could we do? As you can imagine, with 5%, we can do a lot of things. With a little bit more, we can even do much more. Now, whenever you have data, whenever you have this much big data, the question becomes, well, how are you going to treat this data? How are you going to analyze this data? And this is where machine learning comes in. So machine learning, you can really think about it in a very, very simple term as the following. It's a technique or a method that analyzes data to try to figure out some patterns that would give you some prediction or that would give you some information on how you analyze this phenomenon. We have been using machine learning for a long, long time. We have it in cars, we have it in robotics, we even have it in our phones, we have it in medicine, we have it in a lot of things. All of these are forms of machine learning. And because we already have it, the question really becomes, well, if we use it in our cars, in our medicine, our materials, how come we don't really use it that much in civil or fire engineering? This presentation is trying to show you a glimpse of what could we do if we use it. So it's always good to look at your field and then try to see what methods we have now and where are we going. So if you think about the civil engineering industry, you can see we have this chart from McKinsey, and these are established things. This is what we do now. As you can see, we have a lot of things that are established because this is our industry. We have a few things where top firms are looking to hire engineers. And we also have something what we call emerging technologies. Now, both of these two blocks is the future. This is what's going to happen in the next 5 to 15 years. And if you pay close attention, you will see that machine learning is right there. This is where our future is going. This is what we have. This is finite element simulation, performance-based design. This is surveying, drones, robotics. This is what we have now. This is where we're going to be in the future. So because we know we're going towards there, it's always helpful to start and establish something right now, because to go there, we have to start somewhere. So this is our industry. And if you look at the industry, usually the industry follows academia. And whenever we think about academia, we mainly think about publications and we think about patents. When it comes to machine learning, AI, a lot of things started to really happen around the 1980s. We have a lot of publications. Nowadays, we have about more than 150,000 paper a year from computer science, machine learning. Whenever you have applications, you'll have patents, because patents mean that now you can take this knowledge and you can come up with things that you can sell or buy and make, for the industry. So publication rises, patent will rise. This is machine learning in general, computer science. So how does it affect us in structural engineering or in civil engineering? Well, this is where we are now. This is structural engineering. This is a structural fire engineering. You can see the number of publications is much, much smaller, about 250 papers a year. These are the number of papers that are in structural fire engineering and uses machine learning. So from 250 a year to more than 100,000 paper a year, you can see we are very, 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 very small, which is good because now we're starting to grow. This is where the future is going to come. So what we normally do is the following. We have some traditional methods, we have some classical methods. These are fire tests, for instance. If you think about a fire test, costs money, costs time. It works. Sometimes it doesn't work. If you think about a standardized fire test, we have a lot of discussion there, so we can leave that for a different day. But there is a lot of things that go on that builds on physical tests. On the other hand, we also have simulations. We have finite element simulations, finite difference simulations. We have all these different tools. These are computational tools. So basically, to use it, you're going to have a procedure. You're going to have to have a software. You're going to have some form of inputs, material properties, geometric properties, and so on and so forth. If you think about this for a minute, you'll start to realize that when it comes to tests, we rely mainly on the standardized fire tests, whether it's E119 or ISO 834 or its derivatives. When it comes to simulations, we don't really have a standardized way to use finite element. We don't have a standard that says if you would like to use finite element, this is what you do. Most of the way we use finite element is based on us. We build a model, we validate the model against some experiment, we plot two curves, and we think, well, it's close enough, so we have good validation. But in reality, we really have to have a standardized way to use, for instance, in material properties, geometric properties, boundary conditions, solutions, and all those things. So if you think about it, we have different methods. Each method has positives and negatives, which is fine because this is what researchers, this is what the industry is. But it's always helpful to go and start to see what's the next thing that we could do. So in fire engineering, most of our problems, if you really think about them, have a few things that are common. We have a lot of variables. Each variable has a lot of variability. There is some form of dependency, interdependency between variables. And because of all these things, our problems are usually complex. And because they're complex, we have to use assumptions, and this is where we have to use simulations. And to negate all of that, this is a way where we can say, well, okay, this is a lot of data, this is a lot of parameters. Maybe machine learning would be something that we can use. Now, when it comes to machine learning, I'm sure you've heard of a few terms. For instance, you've heard of algorithms, ensembles, surrogates, fitness, types of analysis. All these are terms that are not really civil or fire engineering terms. These are computer science terms. And the simplest way to think about this is the following. An algorithm is a process. It's a way that says, if you have data, this is how you do the steps, step 1, step 2, step 3. It's just some rules, some steps. An ensemble is a group of algorithms. A surrogate is a very, very simple algorithm or a very, very simple procedure. You have fitness metrics. Fitness metrics are the way that we say, okay, well, this algorithm or this model is validated with high accuracy. We have different types of analyses. We have a lot of things. One of the biggest things that always hinders machine learning in our area is the use of coding, because we don't really teach coding that much. So everybody thinks about, well, I don't want to. It's too late to learn coding now. The good news is we don't really have to use coding that much anymore, because all of these things have been already made and validated by computer scientists. Our job is to learn how to use them, apply them to our problems, and we can learn something new from them. So don't think of coding as an issue. Think of coding as something that, will help us to get to use machine learning. And of course, there are many, many algorithms. Just like what we have many different building codes, and each building code has many different methods and tables and equations. Think of these algorithms as the same thing. These are processes or methods or tables or things that would help us solve some data to analyze a phenomenon or a problem. So it's much simpler than it is. So how can we really use machine learning? Well, right now, this is going to be perhaps the second stage of the presentation where we start to show some examples. If you have a fire in a building, the first question that would come to, or one of the first questions that a fire engineer would think about is, well, is the building safe or not? Or how much residual capacity do I have? Is the building is going to collapse, right? So all these are valid questions. Now, how can we use machine learning? Well, one of the things that we can use machine learning in this case is the following. This is going to be surprising, so don't be surprised. I'm going to show you a few things. So this is how, for instance, autonomous cars drive. This is how they see different people. This is how they see different vehicles, traffic lights and stuff. This is how you set up your phone when you first get it. This is how you set up your Face ID, and then your phone understands. This is my face when you see it unlock that. Breathe. There has been some research done in Europe recently, and the idea was, well, if Mona Lisa was a person, how would she talk and laugh? This is a way that we can use machine learning too. Now, if you look at these three different examples, the question becomes, well, how do these three different examples relate to a building in a fire, right? Well, the thing is, it's very simple. Machine learning is like math. It can be applicable to different things. If you can teach an algorithm, or if you can teach a model that this is a car, this is a person, this is a face, this is a painting, then you can easily tell it, this is damage, this is cracking, this is tear reinforcement, this is, for instance, spawning. So in this case, what we did, we took a computer vision algorithm, and we taught it that whenever you see something like this is concrete cracking. Whenever you see dark color like this is basically an effect because you had fire in there. Whenever you see something like this is an indication of spalling. And if you can identify cracking, different failure modes, if you can identify crushing, and you can teach the algorithm that for each failure mode, you can give it some confidence. So basically the algorithm would say, well, I know that this is a major failure with 95% confidence. Then not only you can identify damage immediately, you can also label it and quantify it. And if you can do this, guess what you can do? In reality, the capacity of a structure is really a function of two things. It's a function of your geometry and material properties. Knowing the damage visually is a part of the geometry. You can see how much geometry you have lost. For instance, timber would char, you lose some thickness. Concrete would spall. Steel will have some buckling. Will have some local issues. So you can get this component material. You can also get the same thing because material degradation is attributed or is linked to some changes in color. If you can get changes in color, you know the temperature. If you can get changes in geometry, you can get that geometrical component. If you can have both, then basically you can find the magnitude of damage or approximate it. You can estimate residual strength, and you can do this completely human-free. I think, perfect, thank you. So basically, if there is a building in a country and your firm or your office is in a different country, you can just use the same algorithm there, and you can do all the analysis on the cloud. You don't have to bother with sending humans into a building or a burning building, and it's very cost effective. So this is in general how can machine learning, for instance, help us solve practical problems when it comes to fire engineering. Now, the focus of this presentation is something that's a little bit on following. Well, we had a question, and the question was, well, if machine learning can identify these failure modes, well, maybe we can also use it to find out or discover something new that we haven't learned before. And this is a very simple example. I think, imagine a concrete column. You have a concrete column, it's a rectangular column, you have some concrete, you have some steel reinforcement. If you take many columns and you subject them to standard fire and you start to measure temperature. So in every column, let's say we measure temperature here at the core of this column. It's right at the middle of this column. And from each test, you plot the temperature. What do you see? So we took the same column and we tested many, many times. Well, you'll see a few interesting things. One, you'll see that the temperature will always increase whenever you subject heat. You'll also see that the temperature curve will always curve, will always be some form of a parabolic shape, no matter what the column is. Now, because we can see this, because we can see trends, and because we can see common items within these trends, basically this tells us that whenever we have a column, its temperature would rise, and it would have to rise in a certain shape. Now, this is very interesting because now we know this, and we don't really need machine learning to know this. We know this from physics, we know this from our observations. But what we don't know is what kind of a curve is this? How does this curve change if you change the geometry of the column? How does this curve change if you change the heat, or if you change the material strength, or if you change the concrete type? And this is where we really have to think about now big ideas. For instance, we start to have to think about, well, we have data. We can use statistics to analyze this data. We also have our opinions, our expert opinions. We see tests, we've seen them. The goal is, can I use all of these things to find out a very, very easy way, or a very, very easy tool or a method to map whatever I have to come up with the performance I would like to, for instance, temperature rise or deformation. And this is what we have here. You have some kind of a structural member. You have some kind of performance, temperature rise or deformation or spalling or cracking. To get from here to there, we have to have some kind of a mapping function or some kind of a model. This model could be a physics-based model, it could be a simulation model, or it could be a finite element model, or it could also be a machine learning model. In this case, we're focusing on a machine learning component. So we have to have a hypothesis, and every research is with a hypothesis, and our hypothesis is the following. If we have a phenomena, temperature rise, deformation, falling, and we know that this phenomenon is a function of some features or some parameters, then if we know the features and we know the governing relation or the mapping function for these features, we can easily find the phenomenon. For instance, think of it this way. We have two beams, right? And these two beams are identical. Same geometry, same material strength, same span, same fire, same boundary conditions. The only difference between these two beams is the loading. Beam 1 has a larger load than beam 2. So if you start to think about the temperature rise, both beams will have identical temperature rise because both beams are identical, same material, same geometry. Loading doesn't really add much to the temperature. If you start to think about deformation, well, beam 1, because it has higher loads, it would deflect much, much faster than beam 2. Because it would deflect much, much faster, beam 1 is going to collapse much, much sooner. Now, this is, again, very, very easy to visualize. You only have one parameter to vary. Everything is identical. One beam has higher load, and hence this beam is going to fail early. Now, what if we now start to think and say, well, what if this beam was twice as deep, much, much larger? Would this beam still fail earlier than beam 2 or not? What if beam 2 was shorter? Will beam 2 fail before beam 1 or not? So as you can see, the more parameters we vary, if we vary geometric parameters, material parameters, loading, and boundary conditions, we can't really figure out the mapping between the inputs and outs very easily. We have to use a higher level model. And if you think about, for instance, a test, you will have to conduct multiple tests. If you think about finite element simulations, you have to do multiple simulations, and so on and so forth. When we use machine learning, there is a very good chance that we don't really have to use as many tests or as many simulations to get to the same results, because this governing relation or the mapping function or the thing that makes things happen, if you can get it, then basically you can arrive at all the predictions that you would like to do. So in this case, we again took a model, we trained this model, and this is what we see. The black series is the tests, the red series is the predictions from the model. So if you look here and if you see This is deformation in beam 1 and beam 2. You could say, somebody would say, well, for these two beams, the one from machine learning and the one from the test, we have some good agreement. It's not perfect agreement, but we have some good agreement, which is good. So if you try now to change different parameters within this beam, you can see now if you change, for instance, the depth, your deflection curve will become a little bit more parabolic, and you can see that the machine learning also can figure this out. It's, good predictions. If you complicate the problem more, you can see that we even have now very, very good predictions. So it's very, very simple. The process is simple. You start with a few data. The more the algorithm can see data, the more it understands the problem, the more it tries to become much more better at predictions. Now, all of this without using physics, without using simulations, without using tests. This is a pure data-driven analysis. And eventually, you'll be able to have something like this whenever you have the mapping function. All what it takes is take the function into Excel, drag the function. For instance, this is my function here. And all what I can see is I can get the deformation or the temperature very, very easily. I can do temperature and I can do deformation. Now, the funny thing is, you don't have to do thermal analysis before a mechanical analysis. Usually in finite element simulations, we run a thermal analysis first and then use the temperature results into the structural analysis. When you use machine learning, you can decouple both of them. So you can do these two things separately. As you can see, this is without any coding. And at least this Excel sheet can do 15 members per minute. So if you think about a simulation, usually a simulation takes a few minutes, a few hours once you get the model running. In machine learning, it's much, much faster. It's almost instantaneous. Now here, of course, we have to pause because everything that sounds too good to be true, we have to think about it. We have to analyze it. We're engineers, right? We have to test it. At the end of the day, we're engineers, and we really need to understand how AI works, right? This is why, because if we understand how AI works, then it becomes easy for us to understand the physics behind the problem. So if you start to think about the different ways of how AI really works, you'll see fascinating, stuff. For instance, MIT, the dark secret of AI is no one really knows how the most advanced algorithms do what they do. It's a bit counterintuitive. If you think about the Atlantic, not even the people who write algorithms really know how they work. So this could be scary, this could be interesting, right? Because now you start to think, how can something predicts a phenomenon so well, but we don't really know how it does it. If you look at other opinions, in this case, the black box is nothing to fear. So some people are fine with it, others are not fine with it. And at the end of the day, we really have to understand one thing. For us, we can't just use something blindly. We have to understand how it works. So at the end of the day, we really have to understand and teach others how things work. Now, how things work is basically where we have to sort of think about explainability and we have to sort of think about causality. Now, Mo will talk about explainability. I'll start with causality and then I'll give him the floor. When we think about causality, this is basically why things happen. And I have here this example. I hope you're gonna like it. I have a question. So the question says, does more PhDs in civil engineering lead to more collapsed structures? So does this mean if we have more PhDs in civil engineering, does this mean we're going to have more structures that collapse? So this is a question, and we need to find some data to analyze this question. So what we went to the National Science Foundation, and we get their data, and we went to this very famous paper, and which analyzed how buildings collapse and how much. And we saw this. So the purple line is number of PhDs. The blue line is the number of collapsed structures. This is from 1991 to 1996. You can see that the correlation between both is 85%. So the question really becomes, does having more PhDs lead to more collapsed structure? These are real data, and the data says there is a very, very high correlation. This is a strong correlation by all means. So we don't like this answer because this looks scary. So what we do is we go and look for new data. So the new data that we looked for was for data on bridges. Again, same years, 1991, 1996, same resources, real data. We have now a correlation of 20%. So this is a little bit much more comforting, right? Because now we know that maybe it's not having more pH doesn't cause collapse. Now the funny thing is, in 93 we had a lot of bridge collapses. If you take this data point and bring it somewhere here, this correlation will be 80%. So if 93 is out, this correlation, instead of being 20%, will still be 80%. So this will show the question again, does having more PhDs cause more collapse structure? Now, of course, correlation does not mean causation. And we can easily see this if we start to look at the full spectrum of data. So if you look at data from 1999 to 2000, you can see that we don't really have correlation. Correlation is very, very weak. For building is 35%, for bridges is almost 4%. So does having more PhDs cause more collapse structure? Most likely not. So this example is interesting because of two things. When we use machine learning, we usually use some data. We would say we use this data here in gray. We don't have access to all data. So sometimes our models could be biased. So this is one. Second thing, which is much more important. When we use machine learning, there is a high emphasis on correlation. And as we saw here, having high correlation doesn't really mean that this thing causes this thing. So when you use machine learning, we have to always remember that we need data and we have to be aware that correlation does not imply causation. And this is where using causality becomes very, very interesting in this case, as well as explainability, as Mo will show you. Yeah, so when we use causality, we have to understand that there is a very, very fine line between machine learning, statistics, and causality. When we use statistics, we have to assume conditions. The data we use have to follow certain trends. For instance, if the data is not normally distributed, we can't use, for instance, stable regression. We have to use other forms of regression, or we have to transform the data to be able to use regression. When we use regression, it becomes a little bit more tricky because when you use regression, you already have an equation. You have, for instance, ax1 plus bx2 plus cx3. This form of the equation is already given to you. You did not derive it yourself. Because the form is given to you, basically you have to fit the data to the form. If the form doesn't work well for the data, you're going to have very, very poor predictions. When you use regression, you say this is y and this is x1, x2, x3. In reality, x1, x2, and x3 may not happen at the same time. Maybe x1 happens before x2. So having x1 plus x2 may be confusing because it doesn't really work that way, right? So as you can see with statistics, there are some issues that we have to take care of. And here's a very simple example. We have here compressive strength of concrete, and we have here loading. If you look very, very closely, you see that low strength has very high correlation with low loading. If a column is made from low strength concrete, it cannot carry a lot of high forces. However, if a column is made from high strength concrete, it can carry a lot of loads. It makes sense, right? Higher strength, higher loads. If you apply a third factor, if you start to spalling, you will see that there is spalling going to happen whether you use normal weight or normal strength or high strength. Having the strength, it doesn't really matter that much. So this is the difference between statistics. We look at two factors. When you start to think about causality, we're looking at much more than two factors at the same time. And whenever you start to add layers, you'll start to see some changes in the functions of the parameters as well as in the relationships of these parameters. A very smart man once said, this is Da Vinci, by the way, there is no result in nature without a cause. Understand the cause, and you will have no need for the experiment. So basically, if you know why something happens, you won't have to spend a lot of time or money doing experiments because you already know how it happens, right? So why do you have to keep on doing and spending money on experiments? And to do this, we have to use causality. And this is a very, very simple representation. This is a statistics. This is regression. X1, X2, X3. This is Y. Some phenomena, deformation, temperature, falling. In reality, X1 may cause X2, and X2 causes X3. And maybe we have a hidden factor or something else that causes 1 and 3. And what we do, we assume this. x1 plus x2 plus x3, here's an equation. We have high accuracy. In reality, this is what happens. And you can't get this from regression. You can only get this from using causality. So when it comes to causality, we have to think about a few things. The first level, which we always use, even in engineering, this is called association. You do a test, something breaks, you write it down, you increase the depth of something, and you write down what happens next. We're associating what happens because we're varying one parameter all the time. This is experiments. Same thing with finite element simulation. We vary one. What's a parametric study? If you take a paper and you go for the parametric study section, all what it says is we varied one parameter at a time. Because if we vary two, then we can't really see the difference between which parameter causes what. In causality, this is association. The second level is intervention. This is where we use advanced interventional analysis to start to see, okay, now I'm going to change variables and see what's going to happen. Counterfactual is the much more advanced one. This is where we start to say, well, what would really happen if we had changed this? For instance, you do an experiment and you don't have resources to do a second experiment. So you can use counterfactual analysis to say, okay, well, how would the results of my experiment change if I had used something else? And you can't solve this with statistics, and you can't solve this with simulations. So eventually we get to something called data generating process. This is where A causes B and B causes C. And we have two things. We have causal discovery. This is when we discover something. For instance, the analysis would say, this is the relationship between the factors, and this is why the phenomena happen. And once you know that, you can use causal inference, and this one tells you, now that you have discovered this relationship, you can use it to predict accurately what would happen. So the last time, I think this is, I have two more slides and I'll be done, so Mo, get ready, your turn is soon. I have, this will be interesting. I think a year or two ago, we published this paper, and I did this with Professor Kudur, my advisor. And what we did was, we built a very, very nice machine learning model. And all what we wanted to see is if the model can predict fire resistance in concrete columns. And we did. And as you can see, this is from machine learning. This is, I believe, from, maybe this is from Eurocode. This is from Australian. This is from a different code. And this is from the Australian code. So you can see machine learning really predicts things very, very well. The other codes, they predict with up to 4 hours. After that, they don't really predict as much. So it is what it is. But machine learning predicts very, very well, even for longer durations, which we don't really see in the code. So we start to ask, well, if the machine learning predicts this very, very well, we would like to know why. Because if we know why, we can go back and update our knowledge. So what we did, we did the causal analysis, and this is what we found. The causal analysis says, with the same parameters, let's say concrete cover, reinforcement, length of the column, boundary conditions, eccentricity, loading, width of the column, F prime C, Fy, the same parameters that you use to create this model, if you use the same data and same parameters, there is no way that you can figure out why we can predict this model, this phenomenon causally. So one more time, you can use the same data and same parameter to predict something, but you can't figure out why. Because if you apply causal principles, you need more parameters and you need more data. Now, this could be something interesting / scary, because the model gives you very, very high accurate results, better than building codes, but it cannot tell you why. So as an engineer, you're going to have to ask yourself, will you trust this model and use it in the industry, or will you have to think more about it? So you can see this is a very good research problem when you start to think about, okay, well, now we have to use explainable AI, I have to use causal AI. And we also did the same thing here for columns, and this is what you would see. Let me show you this. So if you use physics, you can predict how the column response will differ if you change the strength, if you change the boundary conditions, and so on. You could use machine learning, you could use causality. Now, the interesting thing is, if you use machine learning, no matter what parameter you change, the machine learning model is unable to tell you how the column will differ or how the behavior of the column will be different. If you use physics, it can tell you accurately how some parameters will change. If you use causality, it will tell you how all parameters will change. So machine learning works for maybe one parameter correctly, all the other ones are not correct in this case. Physics work for a few parameters. It doesn't work well for other parameters. For instance, in this case, this green light, this green series, it says, if you increase the strength, if you increase the reinforcement of the column, you'll have much higher, much faster deformation, which doesn't really make a lot of sense, because if you have more steel, you will have more strength. So you should have much more failure later in time. So this is where Mo's going to come in, and he's going to talk about spalling. As you know, spalling is a very complex phenomena. There are many papers on spalling, many equations on spalling. And Mo, take it home.
Good morning, everyone, and thank you for having us today. In my part of this presentation, I will be going over or diving into the structural fire engineering domain and see where we applied artificial intelligence and explainable artificial intelligence into the structural fire engineering domain, or the fire-induced spawning of concrete. There are a few theories. Before that, let me generally explain what fire-induced spawning of concrete is. We can generally define it as the scaling of a concrete portion or chunks that peels off the concrete bulk when we expose it to fire. There are a few ramifications that are associated with spawning that varies from forming a micro cracks within the concrete portion into anticipating a significant decrease into the concrete capacity. Thank you. So far, there are a few theories that have been proposed to explain spawning. However, none of them is widely accepted. The first one is moisture clock theory, or the vapor pressure theory. It mainly says that if we exposed a concrete member or concrete specimen into fire or elevated temperature, the water will start, the surface water will start to evaporate, and causing the water will start to evaporate and travels toward the center because it's cold in there. And since it's cold in the bulk of the concrete, inside the concrete, the water will start to condense, where the pressure will start to build up. So once it does, and once the pressure keep building up, once we exceed the tensile strength of the concrete, spalling will occur. Now the process will continue after the spalling occur. Water will keep evaporating, traveling toward the center, where it will condense. Once we exceed the tensile strength, spalling will occur again until we lose the integrity of the structure. Now, there are some researchers that contradicted this theory, saying that they have observed spalling happening in samples where the vapor pressure was not high enough to cause spalling, which means that it didn't exceed the tensile strength. So they mainly concluded that the water vapor pressure is not the main reason for spalling. Moving forward to the second theory, which is the thermal stresses theory, it mainly says that if we have a concrete member and we expose it to a sudden influx of heat or a high heating rate curve, as you can see on the right upper right side or upper right figure, you will see that there is a temperature gradient between the surface and just 3 centimeters inside the concrete. This temperature gradient is causing these stresses. The compressive stress will occur at the surface, where the surface will be expanding due to this sudden influx of heat, but the structure is loaded. So the structure will be compressing the concrete, while the the surface of the concrete will be expanding. This is where the compressive stress occurs. Now, in terms of the second one, which is the tensile stress, it occurs due to the first theory. It's mainly related to the water vapor pressure, while the third one, which is the strain incompatibility, it's the incompatibility between the aggregate, which is expanding or dilating, and the cement base that is shrinking due to the loss of water. Now, researcher again contradicted this theory by observing spalling in concrete samples where the heating rate wasn't high enough. So if we expose a concrete specimen into a slow heating rate, they still observed spalling, which means that it's still mysterious. We don't really know how spalling is occurring. Just one more comment to add is that even if we looked at the codal provisions, ACI 216.1 or the Eurocode, we will, in the ACI 216.1, they mentioned spalling once, while in the Eurocode, they have provided one limitation and one recommendation, which is like making us believe that this is a very complex phenomena. Now, can we go to the next slide, please? No, we know that this is a very complex phenomenon because there are many factors that are influencing spalling. These factors are influencing in a non-linear relationships, and these correlations is also these factors are also having correlations between each other. So this is mainly why the spalling is a really complex phenomena. Now, we have conducted a sensitivity analysis where we examined 15 algorithms. We wanted to bridge the gap between having a model that can accurately predict spalling and making sure that this model, by examining many algorithms or models. So we created 15 models, we examined their performance, and we found out that XGBoost is the main or the best performing model by achieving 92% accuracy. Now, to check this accuracy, we also applied confusion matrix accuracy, where if you can see here, the diagonal line, the colored diagonal line is representing the accurately predicted samples, while the white diagonal line represents the missed predictions. Now, now if we go to the next slide, we now have a model and we know that it can accurately predict spawning, but we know that AI in general are black boxes. We don't really know how these models are reaching these predictions. So for the first time, we are applying explainable artificial intelligence into the fire-induced spawning of concrete. And this will help us to bridge, again, the gap between the prediction and providing limitations and recommendations to be able to understand how this phenomenon is happening, or why, or how to limit it, or how to solve it. So we applied a few advanced techniques and explainability tools to help us open that black box and see how this model is reaching this prediction. And these few methods that we will be illustrating to you in this presentations are the summary plot and the partial dependence plot. If we go to the next slide, the summary plot mainly show us the factor or the high impact factor, the factors that are highly impacting spalling in a descending order, meaning said that, for instance, PP fiber, moisture content, maximum exposure temperature are the top 3 influencing factor to spalling. And moving forward, while PP fiber diameter is the lowest, which means that the top factor will be the highest impact, will have the highest impact on spalling, while the lower factor will have the low impact. Now, if we looked on the right side, you will see that there is another layer that has been added to this figure, which is the color. This dots, these dots are instances. Each one of these instances is representing one sample. The red dots will represent higher feature value, while the blue dots represents lower feature value. Let's take an example here so you can understand exactly what this figure is, or you understand how to read this figure. If we looked at the first example, the PP fiber quantity, the red dots represents higher PP fiber, and the red dots are associated with no spalling, which mean that higher PP fiber are mitigating spalling. Now, if we looked at the second one, higher moisture content represented by the red dots are associated with spalling, which mean that, which we already know that higher moisture content will influence spalling significantly. Now, the limitation of this figure is that we don't have limits. Yes, we know the direction of impact. We know what are the key factors or the critical factors that are influencing spalling. However, we don't know the limits at which, if we exceed it, we will be in a dangerous area where the chances of a specimen to spall will be increasing significantly. So to overcome this limitation, we will go to the partial dependence plot, where in this plot, we can see the limit at which the spalling will increase at specific limits. These limits are, for instance, the first figure on the left, the moisture content. The moisture content of 2% is the point where the chances of a specimen to spall will start to increase significantly, which means that the 2% moisture content is a critical limit. Exceeding it will increase the chances, while if we kept it or maintain it, the chances will be at its minimum. Now, if we go to the maximum exposure temperatures, there are a limit at 300 degree and at 500 degree. The main limit is at 500 degree, where if we exceeded the 500 degree, the chances boom up, which means that 500 degree is mainly the critical limit. Again, for the PP fiber, if we added 1.5 kilogram per meter cube, the chances will be decreasing significantly. Also for the heating rate, it's the same thing. Now, all of these limitations, only 4 limitations are being illustrated in this presentation, but there are a table where I tabulated all the limits that I have been extracted from the model that I did, and this table compares between the XAI outcomes or insights that we were able to extract and the main literature, domain knowledge, or whatever we call it, the godfathers of fire-induced spalling, where these people have found all of these insights and we are comparing it. So in another word, we are verifying the domain knowledge by implementing our data into the AI model. Now, what we did in this presentation is showing you a couple of explainability tools that we used and the limits that we did. If you are interested and you want to see it from a local perspective, or where we analyzed a sample by sample and instance by instance and see how the model made that prediction per instance, you can go ahead and look at the papers that we have published and cited down there. Yep. I guess that's all what I have. Thank you so much. And if you have any questions, please go ahead.
Perfect. Thank you, Mo. I think there is also one more slide and then it said we're good. So of course, with every presentation, we have to think about the future and to go from here. As you can see, there is a big and heavy component when it comes to algorithms and how we can use them. So when we start thinking about machine learning, we have to start by our own domain, and we start to have to think about education and think how we can include machine learning into our curriculum. We have to think about databases, and we have to share our results. We have a lot of experiments all over the place, so maybe this is a good time to start to collect databases. We have to start to think about algorithms. Whenever somebody has an algorithm, maybe share it with everybody else so we can expand upon it, so we don't have to reinvent the wheel all the time. We have to test, and learn what machine learning is. And of course, as always, there has to be some form of support between industry and academia, because they can't just work in parallel. They have to work parallel to each other. And as Mo said, we're very happy and very fortunate to be in this seminar and presentation with you. Thank you for being so nice, and we're open for any of your questions.
Thanks, Dr. Nassel. Thanks, Rashid. Yeah. Is there any question from online?
Hi, Muhannad and everyone. Can you guys see me?
Yes, we can. Hi, Anwar.
Hi. I don't actually have questions because you're exceptionally clear, and yeah, so that was a really nice presentation. Just want to say thanks for all this work that you're doing and for the sort of activism in getting the entire community to try and adopt, to actually start using more modern techniques. Can you tell us a little bit actually about the work that you're doing with the ASCE towards promoting this kind of AI and machine learning in civil engineering?
Yes, this is a very good question, Anwar. Thank you. So as you know, ASCE is the American Society of Civil Engineers, and we have, just like any other building code committee, we have different codes and we have different committees. One of the committees is what we call advances in information technology. This is my committee. I'm a chair of that committee. Thankfully for my colleagues. So in that committee, we're trying to see how we can use machine learning in structural engineering. So we're really working very hard to see, maybe start to think about ways where we can say, okay, well, this is now a procedure that if an engineer would like to use machine learning in their firm or in their research, this is like a template that they can follow and they can use. Because as we've seen, we have been using finite element simulation for a long time, for many years, many decades actually. And there is a lot of different ways on how to use a software. Let's say somebody uses ANSYS or somebody uses Abacus or any other software. We don't really have a procedure that's standardized where everybody would use the same methodology or the same element type or the same, for instance, convergence values or even the material properties. In Europe, they use European codes. Here, we try to use mix and match North American codes with properties from European codes as well. So we don't have a standardized way to apply these things. What's scary, or what I always think about is, if you have material properties in a building code, let's say building code X, for instance, let's not give names. Most of these material properties were developed 20, 30 years ago on different materials than we have now, using equipment that were available at that time, not that we have now. So we still use these values and we mix, for instance, new concretes, and we still use the old values. And I don't know if these values are actually comparable to these or not, but this is the only thing that we have, and hence we use it. But this is one of the struggles that we have to deal with. And hopefully maybe machine learning will help expedite this process, because whenever you use machine learning, you have to emphasize using data, and maybe we'll start to update our codes much more often, maybe use new experimental techniques or maybe new experimental data to update material models and so on and so forth. So building codes are interested in machine learning. I know ACI has been very kind to my group. We have presentations there. We will have one this year as well in October on machine learning and concrete. The Masonry Institute was also very kind to us. They supported our research with on machine learning. ASCE was both kind with a new committee. And I know more building codes are a little bit interested, and hopefully it will become a little bit more useful in the future.
Thank you so much, Muhannad. It's really a pleasure that you join us today.
Thank you for
Thanks.
the invitation.
And we get 2 questions from the chatting box. And one of the audience want to know, may he knows what's the database was modeled on and what's different classification models.
Yeah, I
think
think Mo
this
can
question.
answer this.
Yeah, okay. The database that I used was collected from the literature. It was mainly it contains more than 1,000 fire tests, which is the largest spalling database that any like the largest spawning database that exists in the literature. Now,
To date,
the
to
model
date.
to date.
Let's be very clear.
Okay, to date.
Yeah.
Now, the database was modeled on 15 different models. These models are spanning between supervised learning, unsupervised learning, and deep learning. We found out that the top 3 performing models were the LGBM, XGBoost, and Random Forest, which mean that all of them are decision tree based algorithms. These are the models that it was modeled on. I think hope this clarifies.
And
think
we have a another audience. Yeah, I think you answered the first question. He said thanks, and we got another audience. Actually, I have 3 questions, and he said it's really nice presentation, and he gets a couple questions. Firstly, how does the algorithm check the accuracy of the certain relation? That's his first question.
This is a very good question too. So algorithms usually don't, if you use a traditional machine learning algorithm, they would give you relationships. For instance, if you would like to see something more, in this case, to make an example, for instance, it would say for moisture content and the probability of spawning or propensity of spawning, this is the relationship. The machine learning gives you this relationship based on the accuracy of the model. So for instance, this whole model has an accuracy of 92% or 95% or so forth. And based on this accuracy, it come up with this relationship. Now the machine learning model does not go back and see if this relationship is actually true or not, or if it's actually physically correct or not. Because at this point, using this analysis, it's mainly using data, and we're trying to use explainability to explain how the model arrives at accurate predictions. Now, if you would like some relationships, for instance, this relationship, it's physically plausible. So if you go back to physics and fire tests, you can clearly see that whenever water moisture goes beyond 2-3%, the chances of spawning is much, much higher. So by using physics, we can tell that this relationship is likely to be accurate or not. The model itself does not know that by default, unless you start to use physics-informed machine learning or you start to use causal AI. I hope this addresses this question. It's a very good question. It's very neat. Now I also saw. Yeah, go ahead.
And the second question he has is: are there any recommended error functions?
Yeah. So for error functions, the first question you need to ask yourself is this a regression analysis, or this is like a classification analysis or an unsupervised analysis? And based on that, for each type of analysis, you're gonna have some metrics. The things that we are very, very aware of or familiar with is something is, with regression, for instance, mean error square or R square, or these are some of the metrics we commonly use. When it comes to classifications, as Mo showed, Mo, go ahead. What metrics did you use for this classification? Don't be shy.
For this I use so many metrics, but mainly it's the accuracy score, the confusion matrix, the log loss. We implemented the cross validation technique, and many more. But these are mainly the main metrics. AUC score too, the area under the curve score. So yeah.
Yeah. So we have a very nice paper on metrics. I'm gonna throw it in the chat so you can see it. It has metrics for classification as well as for regression. It has multiple metrics. You could use some of these ones, but in general, as Mo mentioned, for a classification analysis, you would like to go with confusion matrix, accuracy, or area under the curve metric. For regression, traditional metrics like R square or R or mean error square. mean average error also would work out. There isn't really any set in stone metrics. And as you can see, this is a very good question because it also addresses Anwar's question of having to standardize machine learning.
And the last question from Akshay is what the recommendation for the sample size?
Recommendation for sample size. So, Mo, do you have something to say?
It's just that it was really frustrating that I remember when we conducted a statistical analysis for our paper, and it was really a very hard question to ask. We went to the literature, we tried to find a lot of, we tried to look at a lot of papers to find a sample size that we can use for our database in order to say that, well, this analysis or this statistical analysis is valid, and for each bin. And I think the last thing that we found was that 30 sample per bin is fine, but I think this is like a variable.
Yeah. So when Mo says per pin, if you have a parameter and you plot the histogram for this parameter, and let's say the histogram has 10 little rectangles, each one of those 10 having 30 in there, in our analysis showed us that this could be something that we could use. I will try to avoid using numbers. I'm not as brave as Mo with numbers. So I would say that if you think of your data set as a table, the more columns you have or the more features you have, the more likely that you will need more rows for these parameters. Now, if you go to the literature, you'll find mainly 3 or 4 hard limits that I never like to use. For instance, there is a very minimum limit of 10 observations per feature. There is another one of 23 observation per feature. There is 30 observation per feature, and there is 100 observation per feature. My advice is these are very general limits. Try to avoid using them unless you necessarily have to go. We know from statistics for regression analysis or for linear regression analysis, somewhere between 10 and most likely 30 is going to be the minimum number of samples. In machine learning, you maybe want to go a little bit larger, but the right answer would always be experiment and report.
Thanks very much. I think we solved all the questions from Akshay. He said thanks in the chatting box. And we got one more question from John, and he said thanks for the presentation. He's just wondering what model you use that can give the features.
Oh, okay. So this is another good question. When we think of algorithms for causality, just like what we have models or algorithms for supervised machine learning, unsupervised machine learning, and so on, we also have different algorithms for causality. In our analysis, we use a number of algorithms. You can really go back to the paper and see all of them. But the ones that stick in my head is PC algorithm, Peter-Clark algorithm. This is one algorithm that we use for sure. We also have causal nexts. We use causal next, and we use 2Y. So these are 3 different algorithms that we use. And just like machine learning algorithms, each algorithm has positives and negatives. For instance, some algorithms, if you use them, although you're using them for causality, but some algorithms, for instance, they assume that you don't have any hidden features or any hidden parameters. Other algorithms, they assume that you do have hidden parameters, and they try to come up with relationships that identify, well, if you use this algorithm, then if you have certain metrics, then there is likely to be that you're going to have a hidden metric there, hidden feature there. For instance, if I go back to this figure here, and this should take a second, this analysis here, this one, in this analysis, we use an algorithm that can identify hidden features. So because we use that, we can see that the algorithm says, well, we don't really have any direct blanks, and there is something missing, and this something is most likely to be some other parameter or parameters that we did not collect data on, or maybe something else that we don't know about. So if you think about it from a structural point of view, having these parameters, loading level, F prime C, Fy, width, eccentricity, boundary conditions are all valid structural parameters. But maybe we have to think about material parameters or something more towards the boundary condition parameters, or maybe something on the heat parameters. You can see here, we don't really have any parameter for heat or any parameter for heat rate or heating rate and so on. So different algorithms should give you different results. Experiment and report.
Thanks.
Thank you. Thank you.
Perfect. Thank you.
And I think we kind of running out of time, but I want to ask one last question. So you for your presentation, you mentioned about the machine learning is quick and accurate, and but the disadvantage is like we don't know how they give this accurate and quick predictions. So we try to study like try to control the inputs, and then you use concrete spoiling case, and you do a lot of like get a lot of data from previously research, but you kind of lack of some data from those paper as well, because it's from different time and from different research. So my question is, can we just combine, or is there another solution is we combine the finite elements method analyze and with use machine learning as a post analyze? Because I thought that will be more we can understand more about the inputs. And
this is a good question. So the answer is, of course, we can combine them. The one that you might want to think about is the following: when we use finite element, or when we use like even a equation in a code, this equation is based on assumptions, or the finite element has elements, and the derivation of these elements is based on assumptions. For instance, you have to assume plane sections remain plane and so on. Because you have these assumptions, this means that any results from this model will always has to conform to these assumptions. So it's not 100% accurate. Now, if you're using something that's not 100% accurate, but it's approximately enough accurate, this is something good, because we have been using this for a long time. Now, what we're trying to use with machine learning in this case, at least what I'm hoping to do, I'm not really trying to use machine learning as an add-on component to solve finite element method. I'm trying to use machine learning to understand the physics of the problem. And I know why this happens. And if I know why, then I don't really need to use finite element anymore. Because the goal of research is to understand why something happens. If you know why something happens, then you can solve the problem very, very easily without having to go with a much more complex analysis. Now, we don't really know where we're going so far, but we're heading into that direction. We're hoping to see a way, or maybe a method or a few methods, where we can use machine learning and to understand why something happens. And if we know why it happens, then we don't really have to use much more complex analysis or even machine learning again, because you know why it happens. If you know why it happens, it's done. So you can design buildings and you can design structures very, very easily. Now, maybe along the way, we will have to combine methods. We have to combine physics or tests with finite element simulations. We have to combine finite element simulations with machine learning. Now, I know there is a lot of research on using machine learning as a way to make the solving of finite element much, much faster. So maybe a good approach would be, will we use machine learning to understand why something happens, and then maybe we can go back to the finite element model and make it much more accurate, or make it better, or we have to fix some of the assumptions. So the playing field is very, very wide open, and I think brilliant minds like yours, like you guys, would help us get to what we are trying to do. It's your time to do research.
Thanks very much. Seems like we got last minute question. Say like, what if we got other classification models and we want to apply to different models?
Yeah, that's a very good question. Mo can answer this because he's working on a paper that's been due for 2 weeks now.
That's a very good question, actually. Now, if we get SVC as the best performing model, I'm telling you that we will be struggling to explain that model. I remember the deep learning model, I used ANN, artificial neural networks, to build a model, and the accuracy was around 82%, which is high. 85, 82%. It was high, it was good, but it was computationally very, very expensive. It took me more than 8 hours to just generate the feature importance plot. And other than that, I don't think that ANN is easily like, we can't implement explainability tools into the ANN, the deep learning, or I think the SVC, because it will take so much time, and I don't think it's applicable to. So we will be definitely struggling there.
If I
Yeah.
may add, I think it's a good question, but here's the thing, Abdul Waris. If you think about machine learning, for instance, used in medicine or in robotics or in aviation, they have data sets that are millions of data. And they can solve it very, very quickly because they have, GPUs and they have parallel processing. In our case, we have 1,000 data points. So the computational time really is not, at least in my eyes, it's not something that I have to worry about that much, because you only have to do it once, and then the results, and then good. But if you're thinking about something that's, let's say, in 10 years from now, maybe we'll have a data set that has, I don't know, 1 million fire tests or something. The good news is the more advances in computations, things tend to be much, much faster. The other news is, if your question is, because I'm not really sure if you're trying to say that SVC by itself or other models, but let's say that you have 5 different models and each model tells you that the most important parameter is something different than the other models, right? This could happen. And it happens because we're using a data-driven analysis to solve a problem. And this is why we're trying to use, for instance, explainability and causality to try to zoom into something that can tell us the essence of the problem, the physics of the problem. Now, what we do then, right? Can somebody say, well, maybe you could use the model with the highest accuracy? This is one approach. Somebody would say, well, maybe you need to use the model that has the results that matches physics. Well, this could also work if the physics we know is correct. If the test we have is actually correct. Remember, whenever we do tests, we also are confined with equipment and the reliability and the way that the equipment work. So sometimes equipment can only give you certain results. Sometimes it can give you certain digits. Sometimes they are only applicable for certain materials or for certain temperatures. So there is a lot of things that go on. And as we said earlier, I think that this area is new, and there is a lot of questions that we don't know how to answer, and this would be a very good time to experiment and test. So if you come up maybe with some results and some analysis, publish it as soon as you can so people can learn, and maybe we can put a pin on this question and move on to the next question. It's a tough question to answer right now.
Thanks very much.
Thank you.
Yeah.
For the message manually to choose a random subset. Well, here's the thing. We're talking about CHAP, so maybe, and there are other methods other than CHAP too that you might want to try. CHAP is usually computationally expensive, but you could try other methods and see, because even if CHAP says something, that doesn't really mean that it's physically plausible too. Or even if Lime says the same thing, it doesn't mean that it matches physics. These are still based on data-driven analysis. So you have to augment the model with some physics and some causality to be a little bit much more closer to the reality that we're trying to solve. But it's a very nice, it looks like this is a very nice thesis in the work, perhaps.
All right, thanks very much.
Okay.
I think we already running out of time, but thanks everyone to join, and I was surprised all the audience is so active today. And
Thank you.
And thanks for your time, Dr. Nasser, and thanks Ali Bashit as well. And thanks using your nighttime and your early morning time to give this such good presentation. And yeah, I mean, we will upload this record to our YouTube channel later on. And thanks everyone to joining, and see you next time. Thanks again.
Thank you all.
See you.
Good morning, good
To
evening.
everyone.
Thank you. Thank you, Anwar. Thank you, Wang. Thank you, Yukio. Have a good day.
Have a good
Thanks,
day.
Muhannad and Al-Bashiti. Bye-bye.
Bye bye.
Bye-bye.
Thank you.